This presentation is on mathematical models for inventory decisions. Inventory is a critically important asset for most businesses, particularly for retail and distribution businesses. Inventory can account for most of the assets that the business owns, even for manufacturing businesses and some service businesses. The inventories of finished goods and other types of materials that those companies own and have to manage are a big chunk of their total asset base. So it's important to be able to make the right decisions when we're managing inventory. Two tools that can help us make the right decisions are the reorder point model and the periodic review system. Both of these tools basically answer the question for a particular inventory item that I am managing, whether that's a spare part, whether that's a raw material, whether that's something like paint or some kind of solvent that's going to be used to support operations. For any type of inventory item, how much do I order, when I have to order the item, and when do I order? When's the optimal or cost minimizing time to do that? When we talk about the reorder point model, we'll talk about two concepts that are related. One is the concept of safety stock, and one is a concept called economic order quantity. The first system or model that we'll talk about is called the reorder point system or the reorder point model. And the reason it's called that is because the reorder point is the point when we should order more material. When I say the point, I mean the point in time, or more precisely, the inventory level of that item that should trigger a reorder of more of that material. And we could be reordering from an external supplier. We could be reordering internally from our own manufacturing facility, from our own distribution facility. Again, if it's a supplier situation, it could be a retail situation where we're ordering from a vendor that we use. Internally, we could be within a factory. One department in a factory could make a material that's used in later operations in the factory. The reorder point model is applicable to any of those types of situations. So basically, we want to identify the inventory level at which point we should place an order for more of the material. So let's kind of break this down a little bit. Let's take a fairly straightforward example. Let's say that you run a restaurant and one of the items that you use is coffee. Let's say actually that you are going to buy a lot of restaurants and you can't really manage this coffee inventory yourself. You have to come up with a decision rule that you're going to give to an employee, or maybe a decision rule that you're going to program into a computer. So you want to remove the judgment from this process and give folks an algorithm that they can use to tell them when to order more coffee. One option, as it says here in the second bullet point, is you could tell them to wait till the current supply of coffee runs out. In that case, the reorder point is 0. When we get down to having no coffee left on our shelves, we order more coffee. Of course, the problem with that is that there's probably a replenishment lead time, so you're going to be out of coffee, of course, between the time that you order and the time that coffee shows up. If the replenishment lead time is 1 week, you're going to be out of coffee for a week, so that's not too smart. So, if there's a 1 week lead time, you could order at the point where you just barely have enough coffee to get you through a week. So if you use 6 pounds of coffee per day and there's 7 days in the lead time, then you use 42 pounds of coffee during the lead time. So if you order coffee when you have 42 pounds left on the shelf, then just about the time that truck is rolling in with your replenishment order of coffee, you should be running out of coffee, and that should work out pretty much perfectly, right? The only problem with that, the only downside to that is that 6 pounds of coffee per day, or 42 pounds of coffee per day, is an average, and sometimes demand might be a little heavier than that average, a little bit heavier than you expected. And if that's the case, you might sell more than 42 pounds during that week of replenishment lead time, and you're still going to run out of coffee. You might just be out of coffee for a day or half a day or maybe 2 days, but you're going to be out. Another thing that you might not know for certain is the delivery lead time. It might be that occasionally the delivery takes 8 days instead of 7 days. So again, you might run out of coffee if you ordered when you had 42 pounds left on the shelf. So we might want to increase our reorder point a little bit. Maybe we increase our reorder point up to 50, and in that case we're explicitly building in a safety stock of 8 pounds of coffee. And that's basically the way the reorder point system works. In the reorder point system, the reorder point is equal to the demand during lead time plus the safety stock. So demand during lead time is just that. It's the demand during lead time, or the average demand during lead time. You can see a couple examples of that here. We're assuming that the lead times are fairly fixed and known in advance. So if this is a situation where the part is demand for the part can be uncertain because there's real limited manufacturing capacity, and lead times could be anywhere from a couple of days to a couple of months, depending on the market conditions, then the reorder point system is not gonna be a very good system for us. Moving to the second part of the formula, safety stock is something that can be calculated mathematically, or it can be established using judgment or by trial and error. And indeed, a lot of times that's what happens with safety stock. In our previous example, our coffee example, we might have just kind of determined over time that as 8 pounds seems to be a pretty good quantity. With 8 pounds, we don't stock out very often. On the other hand, we don't have a bunch of extra coffee, going stale on the shelf. On the other hand, we can use some statistical tools and or statistical techniques to establish the right amount of safety stock. So here's another example just to make sure that we understand that. Let's say that demand is 600 per year. Our lead time is 3 weeks, and we know that just from experience that our safety stock should be about 12. So the reorder point is the demand during lead time, or the demand times the lead time. So if we're going to do this, since our lead time is in weeks, we need to figure out our demand per week. So our demand per week would be the 600 for the year divided by 52 weeks, and then our lead time, and we have a 3-week lead time, so that would be 3 times that quantity, or 35. So our reorder point is going to be 35 plus the safety stock equal to 47. One way to get a little bit better feel of how the reorder point system works is to kind of graph out what happens over time. So here I've got a graph with, this is on the vertical axis, we've got the quantity of inventory that we have in stock. 0 units, 12 units, 47 units, just a few benchmarks that I've established here. And then we have on the horizontal axis kind of moving through time. So let's graph out our inventory, just a hypothetical inventory level. Let's say we start up here around 90 or 100 units, and as we move through time, we have some sales, and eventually we get down to 47 units of this material in stock, and at this point we place a reorder, and that reorder is going to show up after the replenishment lead time. So let's say that the replenishment lead time is represented by this much time, and again we're kind of assuming that that's fixed here. It's always going to be that much time. So let's keep going through time here with our inventory and kind of see what happens. So now we're going to continue to sell product during our replenishment lead time. We get to right here, and this is what we would expect to happen, because remember we said that on average we sell 35 units of this product during the replenishment lead time. So now our inventory level shoots back up to 12 plus whatever quantity we ordered. Let's say that's enough to get us back up to 100. And then we start to go through time again. We're selling product, maybe we go through time where a little bit of time where demand is really not very good, and then we start to sell some product again. Sales really pick up quickly. We hit that reorder point again, that 47 again, so we place another order. That order is going to show up after one lead time, So I want to use that much time again for my lead time. Again, my lead time is fixed, so it's the same width, the same amount of horizontal space every time. And we go through time again. Let's say demand is pretty aggressive. For some reason, it's a little higher than average. And now we dip down below 12. Whoops. But we still don't get down to 0, or we just barely get down to 0. All right, but this is the point in time, fortunately, where our replenishment order shows up, so our on-hand quantity shoots back up again. And that's basically what the way a reorder point system works. If you graphed it out over time, you would see it has kind of this sawtooth pattern. You hope that you never sell so much during that replenishment lead time, during that yellow time, that you dip below 0. If you have the right amount of safety stock, then that really shouldn't happen. So let's talk a little bit more about this safety stock concept. Remember, you can set safety stock using judgment and experience, but you can also set safety stock using statistics. So let's talk a little bit about how you do that. Remember, demand during lead time is an average, and most there's fluctuation around that average, and in most cases, when we have that, the distribution is symmetrical. And about half the time, the actual value of the variable, in this case demand during lead time, is going to be less than the average, and half the time the demand is going to be more than the average. Most of the time it's going to be in this area, near the top of our bell curve. But again, half the time it's going to be more, and half the time it's going to be less. So in this case, since the variable that we're interested in is demand during lead time, half the time demand during lead time is going to be greater than the average, half the time it's going to be less than the average. So what happens if we just order, or we make our reorder point just equal to demand during lead time? Well, we can think about that using the graph that we used last time. Again, we just kind of go through time here. Remember, now our reorder point is 35 because we've taken out the safety stock. We get down to our reorder point here. I'm going to graph in our lead time again. Remember, about half the time, demand is going to be less than average during that lead time. And if that was the case, we'd look like that. We still might have maybe 3 or 4 units on the shelf. Our replenishment order comes in, and we continue to roll through time. Let's say we get down to our reorder point again. We place another reorder. I'm going to graph out my replenishment lead time. Again, that's fixed. That always takes the same amount of time. But the thing that might change is the amount that we sell during that time, because remember, that's an average. So let's say sales are really good. I'm selling more than average now during this. What happens? Boom, I sell out, right? Because I have no safety stock. So from this point over to this point, when my reorder shows up, I'm stocked out, and that's not a good thing. So the way I protect myself against that, of course, is with some safety stock. So before we can go any further with this concept of safety stock, we need to understand a related concept, and that's service level. Remember, what we're really talking about here is stockouts and trying to avoid stockouts, but there's really a couple of different ways to look at the problem. One way to look at it is the percentage of order intervals in which no stockout occurs. Another way to look at it is the percentage of customer orders or customer demands that can be met because we're not stocked out. Let's start with the second example. If you're Amazon.com, every time a customer wants something, every time there's a customer demand, every time there's a customer order, you have a record of it because those come in through the internet, and you can keep track of the total number of customer orders for a particular item or a family of items. And you can also keep track of the total number of times that you were not able to fulfill that demand from stock. In other words, the times you had to tell the customer, sorry, we can't ship that right away. And that would be, the opposite of that would be the service level. The number of times, or the percentage of times that you could fill that demand from stock, would be the service level. The problem for a lot of businesses is, however, that you don't know once you stock out how many customers would have purchased had you had the item in stock. For example, if you go to Walmart and they're all out of diapers, which happens quite a bit, unfortunately, you generally don't tell an employee, hey, if you had diapers, I would have bought them. Usually you can't even find an employee to tell that, and if you could, there's probably no system for the employee to record that data, and so on. So we don't have that data. All we can really understand in that situation is the percentage of order intervals in which no stock out occurs. That's number one. What do I mean by that? Well, if you think about it, under the reorder point system, when we were looking at those graphs before, every time we get to the reorder point and we place an order, we're basically making a bet that we're not going to sell more than the demand during lead time plus the safety stock during that yellow interval. If we bet wrong and we sell more, then we stock out. So what this first definition here is basically the amount of times where we bet correctly. Again, it's the amount of times, or the amount of those yellow intervals, or the portion of those yellow intervals where we did not stock out. So this is the way we're going to look at service level. So with the first definition of service level in mind, we can compute the safety stock required to achieve any particular service level, 90%, 95%, 99%, that we desire with this formula. Safety stock is equal to a z-score times the standard deviation of demand during lead time, where the z-score is the number of standard deviations from the normal table that correspond to the service level that we desire. Again, 90%, 95%, 80%, something like that. This will make more sense if we do an example. So, let's go back to the example that we had before, where we had an average demand of 35 units during lead time. Remember, that was a 3-week lead time, and you can see in the data here, I've just stated the demand 3 weeks at a time, and if you take the average of that, you'll see that that works out to 35 units. We can also compute the standard deviation of this stream of numbers. We can do that fairly easily using Excel. So here I've typed in my information into Excel, and you can see I've also computed the average using Excel's average function. But I can also compute the standard deviation. And to do that, I can just simply use the standard deviation for the population formula. That's STDEVP of this range of numbers, and that's going to give me a standard deviation of about 2.6, 2.57, let's just call it 2.6. So now I've figured out my standard deviation. What I've done over here on the right-hand side of this slide is I've attempted to graph out standard deviation during lead time. We're assuming that variable is normally distributed. In other words, it follows this bell curve type shape, and that's a pretty good assumption. It's probably pretty close to this distribution. And the other thing that I've done here, just to simplify things a little bit, is I've assumed that the average, instead of being 35.2, is actually 0. So in other words, we could subtract 35 from every demand during lead time, and then the distribution on the high side of the demand during lead time would look like this. One standard deviation to the right of the mean would be 2.6. Two standard deviations would be twice that, or 5.2, and so on. Now, using the properties of the normal distribution, remember the properties of the normal distribution are known, we can convert these standard deviations to probabilities. Remember, we've already discussed that there's a 50% probability that demand will be less than the average, or in this case, demand will be less than the average demand during lead time. We're not really concerned about the cases where demand is less than the average, because if demand is less than the average, we're not going to stock out. We're only in danger of a stock out when demand is greater than the average, so we're really concerned about the high side, the right-hand side of this distribution. So there's a 50% chance that demand is going to be equal to or less than the mean, than the average demand during lead time, 35 in this case. What's the probability that demand is going to be equal to, less than or equal to the mean plus one standard deviation of 2.6? In other words, of about 37.5. What's the probability that demand is going to be 37.5 or less? That would be this point right here. One standard deviation to the right of the mean. Well, to figure that out, we need to refer to our standard normal table, and that's in the appendix to your book. Here's a facsimile of that. So, we're interested in one standard deviation to the right of the average, and that is indicated by these z-scores here. In other words, everything in this left-hand column is a z-score. We're interested in a z-score of 1, meaning one standard deviation, again, greater than the mean, greater than that midpoint in the distribution. And this is the value for, right here is the value for 1.00, which is exactly what we're interested in. We read the first two digits, the one to the left of the decimal and the first one to the right of the decimal from this column here on the left, and then we read the last digit from up here at the top. So we're interested in 1.00. That's equivalent to a probability of 0.34 or 34%. Let's go back to our graph. We can put that in there, and we can see that there's an 84% probability that demand is going to be equal to or less than the average plus one standard deviation. Again, that would be about 37.5 units in our example. Let's go back to our standard normal table and see what would be the probability that demand is equal to or less than the average plus two standard deviations. And you can see that the probability value associated with that is 0.47 or about 47%. So we've got 50% to the left plus 47% now to the right. So that would be about 97%. So there's about a 97% chance that demand is going to be less than or equal to the average plus two standard deviations. So that's one side of the coin, where we looked at number of standard deviations from the average demand during lead time in our case, and figured out what service level that would give us, or what the probability of seeing something less than or equal to that number of standard deviations from the mean is. But that's not the way that most businesses look at the problem. That's a good way to kind of begin to understand the technique, but the way most businesses look at the problem is they start with a desired service level, and then they ask themselves what level of safety stock is required to give us that service level, or in other words, how many standard deviations from the mean do we need to be to assure ourselves of achieving that service level. So let's look at an example to get a better understanding of that. Let's say that our company has an objective of a service level of 95%. So that means that during 95% of those order intervals, we don't stock out. Remember, our standard deviation of demand was about 2.6. So given that information, what level of safety stock is required to give us the service level of 95%? Remember that our safety stock formula is the z-score times the standard deviation of demand during lead time. and the z-score is the number of standard deviations from the mean. Remember that the z-score is the values on the headings of that standard normal table that we looked at. In other words, the row headings, the column that's furthest to the left, and the column headings, the row that's up at the top. We get the probabilities from the body of the table. Since the table is concerned with, well, we can think about the table as being concerned with the right-hand half of the distribution. We have to subtract 50% from the service level that we're interested in. So a 95% service level, taking out the left-hand side of the distribution, which accounts for 50%, is a probability of 45%, or 0.4500. So if you go to your table and in the body you look for the value that's closest to 0.4500, and if you don't have one exactly equal to 0.4500, you want to take the one that's just slightly greater, because you want to be conservative here, although if you took the one that was slightly less than, it wouldn't really make much difference. So take the one that's just slightly greater. So if you do that in your table, find the value that's just slightly greater than 0.4500, and then you look over to the left-hand most column, in other words, the row headings, you'll see a 1.6, and if you look up to the above that value, you'll see 0.05. So add those two together, and that gives you 1.65, or a z-score of 1.65. What does that mean? Well, that means that for a probability of 95%, or in other words, 95% of all observations, 95% of all observations are going to be less than 1.65 standard deviations above the mean. So, go back to our formula. Safety stock equals the z-score times the standard deviation of demand during lead time. We take that z-score, 1.65 standard deviations from the mean. We have to convert that basically to units. So one standard deviation of demand during lead time is 2.6. So we multiply those two together, we get 4.3. Again, what does that mean? That means that 1.65 standard deviations is equivalent to 4.3 units. So if we put it all together, we add that 4.3 units of safety stock to our reorder or to our demand during lead time of 35 to get our reorder point. Reorder point of demand during lead time of 35 plus safety stock of 4.3 is equal to 39.3. So if I order when I have 39.3 units on the shelf, that will assure me of having a 95% service level. Here's just a picture of what we just did. We took our 95% service level, which is really equivalent to 45%, or probability of 0.45, above the mean or above the midpoint. We looked that value up, and we figured out that that was equal to 1.65 standard deviations above the mean. So in other words, the distance here from the mean to this red line is 1.65 standard deviations. So we want to know what's 1.65 standard deviations in units. Well, if one standard deviation was 2.6, we just multiply 1.65 by 2.6, and we realize that this is 4.3 units above the mean, as it shows here in red, and that's our safety stock. Okay, let's change gears. So the reorder point model tells us when we need to order. In other words, at what level of current inventory do we need to place an order for a replenishment. It doesn't tell us how much do we need to order. One way to answer the question of how much do I need to order is with what's called the economic order quantity model. The economic order quantity model is a cost minimization model. It tries to minimize costs that are associated with managing inventory. In particular, the costs that it tries to minimize are the holding cost and the order cost, or the setup cost. Holding cost is the variable portion of my inventory carrying costs and those types of costs. The order cost is the cost of placing an order, so that would be the cost of taking inventory, cutting a purchase order, doing a transaction on the internet, sending a fax, whatever it takes to place an order. Or in a manufacturing setup, or manufacturing situation, you might recall from when we talked about manufacturing strategy that one thing that we're very concerned about is setups. So in many manufacturing situations, every time I start a new order on the shop floor, I have to set up equipment, and there's a cost to that, right? There's a cost of labor and whatnot associated with doing that setup. So that's something that's analogous to an order cost in a manufacturing situation. We kind of treat the order costs and or the setup costs the same in this model. I'm just generally referring to them as order costs in the next graph, but you could think of them as setup costs just the same. It just depends on what type of business situation you want to apply this model to. So let's kind of think about these two different types of costs. Think back to our coffee example that we talked about back in the beginning of this presentation. One thing that I can do is I could just order coffee once a year. If I order coffee once a year, my ordering costs will be very, very low, right? Because I'll only be taking inventory once a year. I'll only have to cut a purchase order and do all those other things once a year. So that would be really good if my objective were just minimizing order costs. On the other hand, if I only order coffee once a year, then that year's worth of coffee is going to show up, assuming I take delivery of it all at one time, which is an assumption of this model. And I'm going to have to hold most of that coffee for a good part of the year. If I order a year's worth of coffee, then my average inventory level, the average amount that I have on the shelf throughout the year, is going to be about half a year's worth of coffee. That's a lot of coffee. The holding costs are going to be pretty high. The cost of capital associated with financing that coffee inventory are going to be quite high. There may well be some spoilage. There could be some pilferage. I've got to have the physical space to put that coffee in. So my holding costs, again, would be quite high. I would be, over here somewhere somewhere like this on this graphic. On the other hand, I could order coffee every day, and then I would just be getting just a little bit of coffee every day, just the amount I could use during the day. On average, I would just have about a half a day's worth of coffee on my shelf, so my holding costs would be very, very low, but I'd be placing lots and lots of orders, so my ordering costs would be very high. So if those are the costs that I'm interested in minimizing, those are the costs that I think are relevant to this problem, I want to pick the order quantity that's going to minimize the sum of those costs. And if we graphed out the sum of the costs, it would be the total of these two lines. It would be kind of a U-shaped curve, and it would look something like that. And the minimum point is going to be where these curves intersect. So where my holding costs are equal to my ordering costs, that's going to be the amount that minimizes the sum of those two costs, and that's going to be the cost minimizing order quantity, or the order quantity that I should place every time I place a reorder. That's the kind of basics from a conceptual standpoint of the reorder point, or the economic order quantity calculation or model. Unfortunately, some of the assumptions of the economic order quantity model don't conform to a lot of the situations that we find ourselves in the business world. For example, one thing that I mentioned already was the idea that if we place one order, all the material is going to show up at one time. That often doesn't happen. Many years ago, most of your ordering costs were probably variable costs. For example, you paid a lot for the telecommunications required to place an order. and so on. Today, that's not necessarily the case. It doesn't cost us very much to order something over the internet or even via fax. Long-distance telephone calls are very, very inexpensive in today's environment. There's a good chance that the employee that's checking the inventory is paid a salary or is not somebody that we can just lay off whenever there's not very much for them to do. Another assumption is that only one item is ordered at a time, and very often that's not the case. In our coffee example, we're probably ordering 2 or 3 different kinds of coffee and maybe hot chocolate and different beverage service type items, all from the same distributor. So there's a lot of assumptions that make it a little bit difficult to apply the economic order quantity in real business situations. I think it's still important for you to understand the economic order quantity model because you will see it out there sometimes in business, and when you do see it, you should ask yourself, is this model really being applied in a situation where the assumptions hold up? Another reason why I think it's important to understand the model is from a conceptual point of view. It does do a nice job of kind of laying out the problem. We've got certain costs associated with large orders, we've got certain costs associated with small orders, and we want to find the ideal point. Unfortunately, a lot of times that requires other trade-offs besides ones that we can just kind of pop into a mathematical model. The other mathematical model that we need to talk about is called the periodic review system. Under the periodic review system, we take inventory once a period. So, for example, every 2 weeks, every Friday, every 10 days, something like that. And we order the difference between the quantity that we have on hand when we take that inventory and a target inventory level. This system is basically a system that a lot of individuals just use in their everyday personal lives. For example, if I go to the grocery store every Friday and I make up my shopping list every Friday, as part of making up that shopping list, probably I check the quantity that I have on hand of different items in my refrigerator and my cabinets. And then I compare that to some target inventory level for each one of those items that I've implicitly got in my head. For example, if I'm making up my shopping list and I look in my cabinet and I see that I only have 3 Cliff Bars on hand, and I like to have about 12 Cliff Bars on hand on the day I get back from the grocery store, then I would put 9 Cliff Bars on my grocery list. The difference between the quantity that I have on hand today when I take my inventory and the target inventory level that I implicitly have in my brain for that item. So to look at that a little bit more formally, the target inventory level is equal to the demand during the reorder period plus the lead time plus safety stock. Let's look at an example of that. If daily demand is 20 and the reorder period is 2 days and the lead time is 1 day, then the first part of this expression, the demand during the replenishment or the reorder period plus the lead time is equal to the daily demand of 20 plus the sum of the amount of days, in this case, in the reorder period plus the days in the lead time. So that's 1 day in the lead time plus 2 days in the reorder period, or 3 days. So 20 units a day times 3 days is 60 units. So if you compare this to the reorder point system, in the reorder point system we were just interested in the demand during the lead time. Here we're interested in the demand during the lead time plus the demand during the review period. So if my review period were 1 week, then I would be interested in that plus the lead time. Because our the first part of our expression is interested in the review period plus the lead time, our safety stock is also interested in the review period plus the lead time. In the reorder point system, our safety stock was a function of the standard deviation of demand during lead time. Here in the periodic review system, our safety stock is a function of the standard deviation of demand during the review period plus the lead time. Let's break that down a little bit more on the next slide. gets a little bit complicated because we have to essentially add together the standard deviation of the demand during the review period plus the demand during the lead time. But you cannot add standard deviations. Fortunately, you can add variances. And remember that a variance is simply a standard deviation squared. In other words, if we have the variance and we take the square root of it, that'll give us the standard deviation. So, to add together several standard deviations, what we need to do is convert each one of those standard deviations into a variance and then add them together, because remember, we can add variances. Once we've added them together, we take the square root to get back to a standard deviation. So to look at it in the situation in our example problem, the standard deviation in this situation is 2. In other words, the standard deviation for demand for 1 day is 2. We're interested in the standard deviation for 3 days. A 2-day reorder interval plus a 1-day lead time. So we square each one of those standard deviations. 2 squared plus 2 squared plus 2 squared. Add them up. And that gives us our variance for a 3-day period. To go back to standard deviation, we take the square root of those variances, and that's 3.5. So in other words, 4 plus 4 plus 4 is 12. If you take the square root of that, you'll see that that equals 3.5. Mathematically, that's the same thing as multiplying the standard deviation times the square root of the number of periods that you want to combine. And that's the way that the example's done in the book. I kind of like the first way that I explained it because I think it's a little bit more intuitive. If you understand the fact that you can't add standard deviations, you have to convert everything to variances, this should make a lot of sense. Okay, so the previous slide explained to us how we get the standard deviation for 2 periods combined, the review period plus the lead time. And again, that was 3.5. So that's one part of our overall safety stock computation. The other part of the safety stock computation is to figure out the number of z-scores, or the number of standard deviations that's associated with the service level that we're interested in. So if you go to your standard normal table and you look up the z-score that's associated with 98 minus 50, in other words, you look up the z-score that's associated with 0.4800, you'll see that that's 2.06. So 2.06 standard deviations is going to give us a probability of 98%. So we multiply 2.06 standard deviations times the value of 1 standard deviation in our problem, and that gives us 7.2. So a safety stock of 7.2 is going to give us a service level of 98%. So putting it all back together, we add together that safety stock plus the demand during the review period plus the lead time, and that gives us our target inventory level, which in this case is 67.2. So let's apply that. Let's say that today is an order day. We take inventory. Our quantity on hand turns out to be 40. How many do we order? Well, we order the difference between the target inventory and the quantity on hand. So in this case, we figured out our target inventory level before. That never changes once we figure it out, assuming that the standard deviation of demand during lead time doesn't change and this other stuff doesn't change. We subtract from that the quantity that we have on today, and that means that today we order 27.2 units. take a minute to compare the reorder point system versus the periodic review system. There's some really key differences. In some ways, these two systems are the complete opposite of one another. In a reorder point system, the thing that triggers our reorder is being at a particular level of inventory, whereas in the periodic review system, the thing that triggers our reorder is the clock. 2 weeks have elapsed, or it's Friday, or something like that. So in a periodic review system, you don't need to take inventory all the time. You just take inventory every time that your reorder day or your reorder time rolls around. In other words, once every period. On the other hand, in the reorder point, you've got to always know what your inventory is, because your inventory hitting a certain level is the trigger to place another order. So a reorder point system requires a perpetual count of inventory. Every time we sell a unit or use a unit, we've got to have a system that's capable of recognizing that and subtracting it from our previous balance on hand to get our new balance on hand. That can be kind of a intense thing, a costly thing. It can be a difficult thing to keep accurate. So in some ways, a periodic review system from that standpoint makes life a little bit simpler. In a reorder point system, our order quantity is typically fixed. For example, we might order the economic order quantity every time, and that stays stable, assuming that our order costs and our holding costs stay stable. Or we might order a truckload every time, or whatever quantity is required to get us a 10% discount every time, etc. On the other hand, in the periodic review system, remember that the order quantity is a function of the difference between the quantity that I have on hand today and my target inventory level. So that's going to vary every time depending on the quantity that I happen to have on hand today. That might make life a little bit more difficult, a little bit more unpredictable for my supplier, my folks on the receiving dock, etc. On the other hand, with the periodic review system, the time between orders is fixed, and probably the time between deliveries is going to be fixed as well, if the delivery time is just a function of the lead time, which is fairly stable. On the other hand, with the reorder point system, the time between orders typically varies, because what triggers my order is my current quantity on hand, and I don't know exactly the day that I'm going to get down to my reorder point. So that can also introduce a little unpredictability and instability into the system. If we think about safety stock, which one requires more safety stock? Well, in the reorder point system, the safety stock just has to cover the lead time. In the periodic review system, the safety stock has to cover the lead time plus the review period. So the periodic review system requires a little bit more safety stock. So my inventory levels are going to be a little bit higher in the periodic review system. My inventory turnover then is not going to be quite as well. My inventory carrying costs could be a little bit higher, and so on. A couple variations of these two systems that we'll just talk about real quickly. One is the two-bin system. Two-bin systems are often used for very low-value items, candy, real simple hardware items like nuts and bolts and things like that in a manufacturing setting or even in a hardware store. And with a two-bin system, classically, I literally have two boxes or two bins of a particular material, like let's say a bolt that's a 1/4 inch width, an inch long, 24 threads per inch, and there's two boxes on the shelf. One box is typically behind the other box. People draw from the box in the front of the shelf, and when that box is emptied out, I pull the other box forward, and that empty box is my signal that I've reached my reorder point, and it's time to order another box of material. Another variation is the min-max system. The two-bin system was a variation on the reorder point system. The min-max system is a variation on the periodic review system. The min-max system pretty much works like the periodic review system, except I don't place an order in every reorder interval. Instead, I only place a reorder interval if I'm below some minimum order quantity that I've established. So my target inventory might be 100. That would be my max. My min might be 50. If I'm at my reorder interval and I've got 60 units on hand, I don't place an order. In a classic periodic review system, I would place an order for 40 units, but in a min-max system, I wouldn't place an order because I'm not below my min of 50. Next week might roll around, and now I'm down to 40 units, and if my order interval is weekly, then again, I would check my inventory, 40 units. I would compare that to my min, and I would say, okay, I'm below my min of 50, so it's time for me to place an order. How much do I order? Well, just like in a straight periodic review system, I order the difference between the max or the target inventory level and what I've got on hand, so I would order 60 units. So again, two-bin system is kind of a variation on the reorder point system, and the min-max system is a variation on the periodic review system. With the min-max system, because I'm not placing an order every time, I'm going to wind up placing fewer orders than I would with a straight periodic review system.